All right, let's talk about vectors in the plane. So vectors are quantities that have direction and have magnitude. Some examples in physics are force, momentum, velocity, and displacement. And when we represent these quantities, we use what we call a directed line segment. So you can see here, point P, we call this our initial point, and point Q is our terminal point. We have a directed line segment with an arrow. We can talk about this vector as capital P, capital Q, with a little arrow on top of it. You might recognize this from geometry. It's a bit like a ray, but these are not rays. These do not go on forever. They start and they stop. So this vector that we just saw on the other side can either be represented by capital P, capital Q with a line over it. Sometimes you'll see them written in text with bold letters. Obviously, we can't handwrite in bold, so when you're writing about them on paper, you need to do the little arrow on top of it. The magnitude of the vector is simply the length of the vector. And the magnitude is represented by these double bars around it. It's a little bit like absolute value, but it's not absolute value. It's the length of the vector, and we use the double bars around the name of the vector. Now, this vector here, you can see it's labeled with a U, and that U is bold. So this vector could be called vector U, like that with the bold font, or you could write it as U with a little line over it. And notice that this is a lowercase letter. We tend to use lowercase letters if we are naming a vector with just one letter. The magnitude of the length of that vector would then be the double bars around the name of vector U. Again, when we're writing about vectors, initial point is sometimes called the tail of the vector, and the terminal point is sometimes called the head of the vector. Sometimes it's called the tip of the vector. It might be helpful to remember the head of the vector by like the word arrowhead. So arrowhead, that's where the arrow is, and so that's going to be your terminal point. So let's talk about equal vectors. Well, equal vectors, as you can maybe imagine, have the same magnitude and direction. This means that they will be parallel, so that's the same direction, that they're parallel, and equal in length, because the magnitude is the length. So equal vectors are essentially translations of one another. So here you can see three parallel vectors on the screen. Opposite vectors, as you can maybe guess, opposite vectors have the same length, but opposite directions. So here we have a vector, one vector that's going from B to A, and another vector that's going from A to B. Their length is the same, but the directions are exactly the opposite. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. I'd like you to identify which of the vectors here are parallel, which ones are equal, and which ones are opposite. So on this screen, vector A is parallel to vector B, and they are both parallel to vector C. And those are all parallel to vector E, which is also parallel to vector F. Remember, parallel vectors have the same or opposite direction, but not necessarily the same magnitude. Equal vectors. The equal vectors on the screen are vectors A and C. So we can say vector A is equal to vector C. None of the other vectors on the screen are equal to each other. B and F are opposite, so we can say vector B is equal to the opposite of vector F, or we can say vector F is the opposite of vector B. We have other opposite vectors, such as A and E, and also vector C is equal to the opposite of vector E. Component form of a vector. So when we talk about a vector in standard position, okay, we talked about standard position with our unit circle and trigonometry, but now with standard position, kind of not that different, is when the initial point is at the origin. So a vector that's in standard position can be uniquely represented by the coordinates of its terminal point. So you can see here that this vector P to Q, it starts at the origin and it ends at 3, 2. So we could say that vector U is, and we're going to use pointy brackets, 3, 2, pointy brackets. You can see them typed right here. So vector U can be just written as pointy brackets, X, Y. Now here's something that's kind of crazy. Well, maybe not crazy. Vector S starts at R and goes to S, and you can see the initial point is at 1, 2, the terminal point is at 4, 4. This vector is equal to vector U, so we can also say that vector V has components 3, 2. Basically, that means that from the initial point, you travel over 3 units and you travel up 2 units, and then you get vector V. So remember, equal vectors, they have the same direction and the same length. So vector V and vector U are equal vectors. They are translations of each other. So if you were to take vector V and you were able to pick it up and shift it so that the initial point is on the origin, it would be right on top of vector u. So that's why they have the same component form. So in general, the component form of a vector with the initial point p that's at x1 comma y1 and q that's at x2 comma y2 is going to be, we'll say vector p comma q, capital letters there with the arrow above, will be equal sign, open pointy bracket, x sub 2 minus x sub 1, comma, y sub 2 minus y sub 1. If I go back over here, what we're saying is, if I want to figure out how far over and up I need to go to get from the initial to the terminal, I can just subtract, right? I can say, well, 4 minus 1 is 3, and then that 4 minus the 2 is 2. So hence we get the 3 comma the 2. So that's why we are subtracting the terminal minus the initial. On this screen, I'd like you to pause the video and write the component form of vector v and vector u. All right, you should have figured out that vector u's component form is 5 comma negative 1. And this one, not that difficult because the initial point is already at the origin. So you just have to figure out the coordinates of the terminal point, which is at 5 comma negative 1. Now vector v, you could just count because you have the picture of it. So vector v, the initial point is here at negative 2 comma positive 1, and the terminal point down here at negative 5 comma negative 5. So you want to figure out how far over do you have to go. So you're going left 1, 2, 3, and you're going down 6 to get there. So the component form for that one would be negative 3 comma negative 6. You also could take the coordinates of the initial point and the coordinates of the terminal point and then just subtract. So you would have the negative 5 minus the negative 2, comma, the negative 5 minus the 1. And then if you did, and your pointy brackets there. And so if you simplify that, you would get what we have there for vector v. What if I wanted to find the length of each of these vectors, the length or the magnitude of each of these vectors? We could use either the Pythagorean theorem or the distance formula, which is actually based off of the Pythagorean theorem. So in other words, we could take the vector here and we could create a right triangle. And so we know that the vertical component here is 6 and the horizontal component here is 3. And I'm not considering direction, so that's why I didn't put a sign on it, didn't call them negative. And we just want to figure out what would be the length of that hypotenuse of that right triangle I created. So you can do the Pythagorean theorem. So let's write that down. The magnitude of the vector p to q, where the initial point is x1 comma y1 and the terminal point is x2 comma y2, is given by square root of x2 minus x1 squared plus y2 minus y1 squared. So this is actually directly the distance formula. You may remember that from your geometry class. And of course, notice out here that I put those double bars around the name of my vector to indicate that I'm finding the magnitude. Now, if you had a vector that was already in component form, now notice that vector p to q, it's not given in component form. We just have the initial point and the terminal point. If it's already in component form, then it's simply going to be that the magnitude of vector A, the square root of a sub 1 squared plus a sub 2 squared. Let's practice this. Here we go. We want to find the component form and the magnitude of vector V that has an initial point of 4 comma 7 and a terminal point at negative 1 comma 5. I included the grid here in case you wanted to plot the vector to look at it, but you don't have to. But I went ahead and drew it in case you want to see it. So the component form will be negative 1 minus 4. So we're subtracting the x components, negative 1 minus 4, the terminal minus the initial, comma, 5 minus negative 7 in those pointy brackets. So simplify that to be negative 5 comma 2. Whoops, 12, I mean. And of course, you can look at the picture and you can conclude that to get from the initial point to the terminal point, you have to go left 5 units and you have to go up 12 units. Now, for the magnitude, because we now have the component form, we don't need to do the whole distance formula. We can just do the square root of negative 5 squared plus 12 squared. And that's going to work out to be 13. And there's your magnitude. Vector operations. First, we're going to talk about doing vector addition geometrically. Now, there's two methods that are popular with adding vectors geometrically. One of them is called the head-to-tail method, sometimes called the triangle method, and the other one is called your parallelogram method. To find the sum using the head-to-tail method, you're going to draw vector A, and then at the head of vector A, you're going to draw vector B. There is vector B that's given, and then we're going to join the tail of A to the head of B. So basically, it's going to look like this. So I'm going to take vector A, like so, and then I'm going to take vector B, like so. I'm going to label these, and then we're going to join the tail of vector A to the head or the arrowhead of vector B, and that is vector A plus B. So that's one method that's pretty popular for adding vectors. The other method, called the parallelogram method, is you're going to place your vectors tail to tail, and then you're going to create a parallelogram. So basically, I'm going to do another vector A up here and another vector B over here, and then the diagonal from there is vector A plus B. So that's another method. If I'm hanging out on a Friday night, I tend to just use the head to tail method when I'm adding vectors. I tend to not use the parallelogram method, but if you look at other sources online, you might see that method. Now, for subtracting, I'm not going to go into detail about this, but basically subtracting vectors is adding the opposite. So you can see here, I took vector A, and then at the head of vector A, I drew the opposite of vector B, so it's just going in the opposite direction. And so then down here is my vector A minus B. So this one is the head to tail method, and then this one's your tail to tail method, where, I mean, I guess you could say that you're drawing the opposite. If you did that parallelogram, you're doing the opposite diagonal of the parallelogram. But again, I tend to not do that parallelogram method if I'm hanging out by myself drawing vectors. So this one is the head to tail method, and then this one's your tail to tail method, where, I mean, I guess you could say that you're drawing the opposite. If you did that parallelogram, you're doing the opposite diagonal of the parallelogram. But again, I tend to not do that parallelogram method if I'm hanging out by myself drawing vectors. So take a minute and draw the two vectors. So it's basically two parts. You got vector P and Q over here. That's like question A. And then over here, you got a different vectors P and Q. So go ahead and practice drawing the vectors P plus Q. All right, so you should have gotten this. You'll notice that it's really important to do these, like you'll be given grid paper to do these. So for vector P, you can count that is over 1 and up 3. So I just repeated here in red and over 1 and up 3. And then at the head of vector P, I drew vector Q, which is over 2 up 2. So I went over 2 up 2, and then I connected the tail to the head. And then same thing over here for this vector P, I counted that it's over 5, 1, 2, 2, over and up 3. So I repeated down here in red, 1, 2, 3, 4, 5, 1. And then I drew the top there from the head of vector P. I drew the tail of vector Q, and it went left 3 and up 3, 1, 2, 3. There's vector Q, and then I draw from the tail to the head to get vector P plus Q. Now let's talk about vector addition in component form. So we're talking about vector A, which has components A sub 1, A sub 2, and vector B has components B sub 1, B sub 2. So I'm showing you a connection here between the geometric drawing of them. So here's vector A. So it has horizontal component A sub 1, vertical component A sub 2. And then vector B has the horizontal component B sub 1 and the vertical component B sub 2. And then here in blue is the vector A plus B. And you can figure out that it has the horizontal component of A sub 1 plus B sub 1 and the vertical component of A sub 2 plus B sub 2. So let's write that down here, that A plus B is actually A sub 1 plus B sub 1, comma, A sub 2 plus B sub 2, close that pointy bracket. So this might remind you of matrix addition, that you are just adding their components. And similarly with subtraction, you just subtract their components. Now scalars, we also did scalars when you learn matrices. If you've learned matrices, it's okay if you haven't. Scalars are quantities that are fully described just by magnitude alone. There's no direction. So time, energy, speed, and distance, these are all just scalar values if you take a physics class. If you're going to do scalar multiplication geometrically, like if you have vector A here, what do you think vector 2A would represent? What do you think the vector negative 3A would represent? Well, vector 2A would just be vector A plus vector A. So here we have vector A repeated twice. So vector 2A would be twice as long, but in the same direction. And then negative 3A would be 3 times the opposite of vector A. So here's vector negative A 3 times, and there with the opposite direction of vector A and 3 times the magnitude is vector negative 3A. So scalar multiplication in component form, if vector A has components A sub 1, A sub 2, and K is a scalar, then K times vector A, you can probably imagine, is simply going to be K times A sub 1, comma, K times A sub 2 in the pointy brackets. So all you're doing there is you are multiplying each component in the vector by that scalar. This might remind you of multiplication, scalar multiplication with matrices. It's the same process. So on this slide, I'd like you to pause the video and try these problems. For question A, because you're subtracting these vectors, you're going to do the x component of vector W minus the x component of vector V, and then the y component of vector W minus the y component of vector V. This can get a little bit confusing because it's kind of the same process. Well, I mean, it kind of is the same process of when we were finding the component form of a vector when you were given just the initial point and the terminal point. We're not doing that here. We actually have the component form already of two separate vectors. So it can be a little bit confusing to keep that straight in your mind, because like what we were doing earlier was we had a point P, which had coordinates x sub 1, comma, y sub 1, and point Q had coordinates. Notice my use of parentheses here, x sub 2, comma, y sub 2, and we were trying to find the component form of vector P. So you have to be careful about what your question is asking you for. So vector V and W, these are already vectors, are already in component form. We're just subtracting two separate vectors, as opposed to having 2 points. We're trying to write the component form of one single vector. All right, go ahead and pause the video again and try problem B. All right, so for here, vector V, I just repeated it here, and then I did 2 times vector W, so I just went ahead and multiplied their components by 2, and then I'm going to do the x, add the x components and add the y components, and so my answer is 4, 13 in the pointy brackets. All right, some of the properties of vector addition and scalar multiplication. This is from page 425 of our Larson precalculus textbook. So vector addition is commutative, just like in the real numbers. This one is the associative property. So you can either add vector u and v and then add in the w, or you can do the v and the w and then add in vector v. You can have a zero vector, which, as you can probably imagine, is going to be a vector whose components are just 0. So basically 0, 0. So if you took some vector u and you added vector 0, the 0 vector, you're just going to get vector u again. So this is all so far just like the real numbers. If you had vector u and you added the opposite of vector u, then you would get the 0 vector. So 2, 3 plus -3, 2, -3 is going to give you 0, 0 as the 0 vector. Then we start working with scalars here. So if you had a scalar that was c and another scalar that was d, notice that these are italicized, these are not bold, times vector u, you could either multiply the vector times the d scalar first and then multiply by the c scalar, or you can multiply the two scalars and then multiply them both by vector u. You'd get the same results. Over here is sort of the distributive property, where you could take a vector and multiply it by each scalar and then add, or you can do multiply or add the scalars and then multiply by vector u. So over here, now this time we're doing two separate vectors, u and v. So you can basically distribute those and say that you can do the scalar c times vector v plus the scalar c times vector. Down here, if your scalar was 1, of course, you're just going to get the same vector back again. If your scalar was 0 times any vector, you're going to get the 0 vector. And then this is a very interesting one, that you're going to take a scalar. If you're going to do the magnitude of a vector multiplied by a scalar, it's actually the same thing as the absolute value of the scalar times the magnitude of the vector. We're actually going to see that in our next example. So here we have vector u and vector v, and we're going to find the magnitude of 3 times vector v. What we can do is that property we're just talking about. We can call that the absolute value of vector the 3, the scalar, times the magnitude of vector v. So that's going to be 3 times, and then the magnitude, remember, is going to be the square root of the sum of the squares of their components. So -2 squared plus 5 squared. So that's going to be 3 times the square root of 4 squared by 5 plus 25. So that's going to be 3 times the square root of 29. We did get a single number when we did this, because remember, we were trying to find the magnitude, and the magnitude is the length. So it makes sense that we now know that the length of this of 3 times this vector v is this number 3 root 29. Now for part B, same thing. You can do the absolute value of -5 times the magnitude of vector u. So that would be +5 times the square root of 1 squared plus 3 squared. So that's going to be 5 times the square root of 10. Now, I want to point out that you could, if you wanted to, you could distribute the scalar inside the vector and then find the magnitude of that new vector being multiplied by the scalar. So let me show you that in action. So if I did -5 times vector u, I'm going to have -5, comma, -15. And then I would do the magnitude of that, which would be the square root of -5 squared plus -15 squared, which is going to be the square root of 250. But then you have to simplify your radical. So now it's more work, because we have to find a perfect square that divides in 250. It's not that bad, because it's going to be 25. So then it becomes 5 root 10. So I would recommend that you go ahead and take the scalar out and do the absolute value of it, because then you don't have to worry about reducing your radical. I mean, this doesn't mean that you will never have to simplify your radical, but if you did have to simplify your radical, it would be a smaller number to deal with compared to something larger like 250. Our last example here, we are given vector u, which has components -2, vector v has components 2, -6. We want to find the values of a and b, so these are going to be scalars, such that when we add those scalars times those vectors, we're going to get a result of -10, -2. I'm going to go ahead and say I have A times -2, comma, -2 plus B times 2, -6, and that's going to be equal to -10, comma, -2. Let's go ahead and multiply these scalars through. So I'm going to have -2a, comma, -2a plus 2b, comma, -6b equals -10, comma, -2. Then we can add their components, right? So the x components, we'll add those, and the y components, we'll add those. So I have -2a plus 2b, or not 2b, comma, -2a minus 6b, close the pointy brackets, and that's equal to -10, comma, -2 in pointy brackets. So now what we'll do is we'll take the x component of this vector and set it equal to the x component of this vector. And same thing with the y components. So we have -2a plus 2b equals -10, and -2a minus 6b is equal to -2. You know what we have here? We have a system of equations. We have two equations with two unknowns. So this takes us back to Algebra 1, where we can solve the system using elimination. So I'm going to go over here. I'm going to line them up. I'm going to choose to I don't know, I'll multiply this top one by -1. We'll say multiply that one by -1. So now I have positive 2a minus 2b, or not 2b, equals 10. I don't need that one anymore. And I'm going to add these two equations, and that's going to give me -8b equals 8. So b will equal -1. I'm going to highlight that because that's one of my answers. And then also, I need to find a, so I can take this b value and plug it into either one of these. It doesn't matter which. I'll do the first one because it's closer. So I'm going to have -2a minus 6 times -1 equals, and so a equals -4. Voila.